Welcome to this comprehensive guide on understanding structs versus classes in C# for Unity 3D, a crucial topic for every beginner programmer and game developer. This video will demystify these fundamental concepts, providing a step-by-step explanation and practical demonstrations within Visual Studio and the Unity 3D engine. We'll explore their core differences, how they handle memory, their performance implications, and when to use each effectively in your game development projects. Let's begin by understanding the foundational concepts of value types and reference types, which are essential for grasping structs and classes. In C#, value types directly contain their data, meaning when you assign one value type variable to another, a copy of the data is made. Examples of built-in value types include integers, floats, booleans, and characters, which are fundamental data types. Reference types, on the other hand, store a reference to the data, not the data itself. When you assign one reference type variable to another, both variables will point to the same location in memory. Classes are the primary example of reference types in C#, and understanding this distinction is key to effective programming. Now, let's dive into structs. In C#, a struct is a value type, primarily used for small data structures that do not require inheritance. Structs are allocated on the stack, which is a region of memory used for static memory allocation. This stack allocation makes structs very efficient for small data, as memory management is handled automatically and quickly. Let's demonstrate creating a simple struct in Visual Studio. We'll define a point struct with x and y coordinates. When we create an instance of this struct, like point p1 equals new point, memory is allocated directly on the stack. If we then assign point p2 equals p1, a complete copy of p1's data is made and stored in p2 independently. Changing p2.x will not affect p1.x because they are entirely separate copies. Structs are ideal for representing small, immutable data, such as vectors, colors, or simple coordinates, where copying is desired. Now, let's shift our focus to classes. In C#, a class is a reference type used for more complex objects that often require inheritance and polymorphism. Classes are allocated on the heap, which is a larger, more flexible region of memory managed by the garbage collector. Heap allocation allows for objects to persist longer and be accessed from various parts of your program, but comes with the overhead of garbage collection. Let's create a simple class in Visual Studio, similar to our struct example. We'll define a player class with a name and health. When we instantiate a class, like player P1 equals new player, an object is created on the heap, and P1 holds a reference to it. If we then assign player P2 equals P1, both P1 and P2 now refer to the exact same object on the heap. Consequently, changing P2.health will also affect P1.health because they are both manipulating the same underlying data. Classes are suitable for larger, more complex objects that represent entities with behavior, like game characters, inventory systems, or managers. Now, let's summarize the key differences between structs and classes to solidify your understanding. Structs are value types, allocated on the stack, and are copied by value when assigned. Classes are reference types, allocated on the heap, and are copied by reference when assigned. Structs are generally faster for small data due to direct stack access and no garbage collection overhead. Classes can be slower due to heap allocation and the involvement of the garbage collector, especially with many small objects. A crucial tip: avoid making structs mutable if possible, as unexpected side effects can occur when copies are made. For performance, passing large structs as method parameters can be inefficient due to the copying overhead. Consider using in or ref keywords for passing large structs to avoid unnecessary copying, optimizing your code. Now, let's see how these concepts apply directly within the Unity 3D engine. Unity's built-in types like Vector2, Vector3, Quaternion, and Color are all structs. This design choice leverages the efficiency of structs for small, frequently used data that benefits from value semantics. For example, when you assign transform.position equals new vector3, a new vector3 struct is created and its values are copied. If you retrieve vector3 current pos equals transform.position, current pos is a distinct copy. Modifying current pos.x will not change transform.position.x until you explicitly assign it back. Classes are used for game objects, components, scriptable objects, and other complex entities in Unity. When you get a reference to a game object, you are working with the actual object on the heap. Any changes made through that reference directly modify the original game object. This behavior is crucial for managing game state and interactions between different parts of your game. So, when should you choose a struct over a class, or vice versa, in your Unity projects? Use structs for small data types, typically 16 bytes or less, that represent a single value. They are excellent for immutable data where you want value semantics, meaning you want copies rather than shared references. Examples include custom vector types, color definitions, or simple configuration settings. Choose classes for larger, more complex objects that require identity, inheritance, or polymorphism. They are ideal for entities that need to be managed by reference, such as game characters, inventory items, or AI agents. Classes are also necessary when you need to use null to represent the absence of an object. A helpful tip: if you find yourself needing to inherit from a base type or implement an interface, a class is almost always the correct choice. Another tip: be mindful of boxing and unboxing when converting between value types and reference types, as this can incur performance penalties. Understanding the nuances of structs and classes is a cornerstone of efficient and robust C# programming in Unity. By applying these principles, you can write cleaner, more performant code, leading to better game experiences. We hope this detailed comparison has provided you with a solid foundation for making informed decisions in your development journey. Thank you for watching, and happy coding!